If you've listened to Technology Untangled before, you'll know that we don't normally talk about HPE tech and the work that we do. But sometimes a customer will ask us to help out with a project that's just too cool not to talk about. And today, we're exploring something that is beyond cool. Beyond our terrestrial limits, even.
A customer asked us if we could take one of their computers and put it on a rocket and deliver it to a spaceship.
And if you haven't guessed already, that client I so subtly hinted at is NASA. Yep, that NASA. And they're bringing the power of high-performance computing to the final frontier.
Much of their mission that they perform here on Earth with their computers in their labs would not be possible when we get to the moon or the Mars due to the distance and the time it's going to take to download the data to be processed.
On today's episode, we're looking at the tech in space that'll make missions to Mars possible. We're going to be finding out what it is that makes sending the latest supercomputers into space so difficult, why we need edge computing on the International Space Station and beyond, and we'll learn about some of the cutting-edge science and experiments happening on the International Space Station as we speak. All this and much more. I'm Michael Bird, and this is Technology Untangled. Humankind has always had a fascination with space exploration, but in recent years, this fascination has really, taken off. Private companies have developed reusable thrusters, and some are even able to launch billionaires into orbit. But the real goal in everyone's mind is getting to that mysterious rust-coloured rock. You know the one I'm talking about. It's Mars. And to get there, we're going to need more than just bigger boosters, because according to the pros, what we really need is spaceships with supercomputers. And here to explain why this isn't just some sci-fi daydream is Senior Vice President and Chief Technology Officer for AI at HPE and Technology Untangled regular, Dr. Eng Lim Goh. So, Dr. Goh, why do we need supercomputers in space?
They were thinking of for human mission to Mars. Just give you an idea, right? If you have a distance from Earth to this International Space Station, Moon is 1,000 times farther away than that. How about Mars? Mars is going to be 1,000,000 times farther away than that, at such long distances, if you are near Mars and you call Earth to say hello, right? That hello is going to take up to 20 minutes to arrive. And then for another 20 minutes for from Earth to say, yes, what I can do for you, for that reply to return, right? So imagine those massive distances and high latency of communication. Astronauts, as they near Mars or are on Mars, will need to be more and more self-sufficient.
So the end game is to put people on Mars. However, we're not quite ready yet to strap anyone into a rocket and send them on their way, thanks in part to this immense data lag. But how do we know supercomputers will have the solution to this self-sufficiency issue? Well, Dr. Goh mentioned something that might be able to help: the International Space Station, or ISS for short. Yes, a mere 400 kilometres above our heads, orbiting the Earth at a blistering 28,000 kilometres an hour, is the ISS, a space-dwelling laboratory dedicated to carrying out all manner of extra-terrestrial experiments, making it the perfect testbed for any interplanetary tech. So back to the issue of self-sufficiency. What is it we actually mean? Well, on one side, self-sufficiency for an astronaut means being independent and getting answers from a computer locally, rather than from mission control. But on the other side, it means having a computer that can essentially take care of itself.
This computer needs to be also self-sufficient on its own. Therefore, it needs to be autonomous, right? We cannot expect astronauts to be, fully trained on the IT side to maintain this computer. For example, on the space station, although I got a lot of volunteers of our support engineers to fly up there to service the computer if it breaks. No, right? It needs to be autonomous, and the computer needs to be able to take care of itself as much as possible.
Well, annoyingly, there goes my ticket to space. Anyway, fun fact, HPE was already supplying high-powered computers to NASA, which begs the question, why couldn't they just build them the biggest, beefiest, fastest, coolest, space-ready supercomputer and just blast that up to the ISS?
We're thinking that, can we launch a few nodes of the high-performance computer that is currently on Earth, and will they work reliably? With zero modification. That was the other motivation, right? Zero modification, because if you start to modify something, it will take time, and therefore, by the time you launch, you won't have the very latest high-performance computers with you. But if you don't do any modification, you can take the very latest with you and launch.
Most people might shy away from the task of making the latest off-the-shelf high-powered computing components ready to withstand cosmic radiation and the countless other perils of space travel, but not Dr. Goh and his team. And so in 2014, he and his team started working on the Spaceborne Computer.
Back in summer of 2014, I had a discussion with Dave Peterson of SGI, now HPE, who eventually became the lead hardware lead for Spaceborne Computer One. And by December of 2014, I wrote a one-page proposal, sent it up to NASA. They agreed, approved it. And by July of 2016, I needed a software lead. And that was when Mark Fernandes became the software lead for Spaceborne Computer One.
Well, we've been asked, how does it compare to the processors that are on the space station and the processors that were used in Apollo? And I think we can safely say we're over 1 million times faster.
Cool your thrusters there, Mark. We'll get to that later on.
With approval from NASA, Mark and his team developed the software for autonomy, while Dave and team got the hardware together to put into the locker that they built. In late 2016, early 2017, HPE completed the acquisition of Silicon Graphics. And I, as Principal Investigator for Spaceborne Computer One, had to approach HPE and, I had to make a good pitch, right? So that the acquiring company would continue supporting this project, yeah. But, I realized I didn't have to worry because Antonio at the time has this foresight to immediately say yes before I could complete my pitch.
And so the creation of Spaceborne Computer One began with the off-the-shelf zero modification ethos firmly in mind.
During Spaceborne Computer One, I was asked if I would allow even the power supply, the AC power supply, to be replaced with a DC one. Because the space station runs on DC power. Why? Because it only depends on solar panels. So I was asked if I would just make one modification, right? I said no. Zero modification means zero modification. The minute you start to say a little bit yes, you cannot claim 100%, 0% modification. And true enough, glad we did that. And NASA supplied therefore us an inverter to convert their DC power to AC one.
But what does keeping these supercomputers truly off the shelf and free from adaptation mean for their longevity? Well, one of the main culprits of computer failure in space is radiation, and resistance against it was just one of the factors Dr. Goh and his team attempted to solve in Spaceborne One's design.
Well, for example, memory is very sensitive. You have a piece of data that is very important. Say, for example, you run a computation and then the application says the answer is yes, or the answer could be no, right? Very important whether it's a yes or no. And the difference is only one bit in your memory being a 0 or a 1. And it's been known that radiation can cause these bits to flip from a 0 to a 1 or a 1 to a 0, right? So that illustrative example alone can tell you this is pretty tricky. If you are dependent on making a decision for this set of computation, there are a lot of safeguards, right, being put in already for standard off-the-shelf computers, like error correction capability, error checking capability. To self-correct, they can't. They can at least tell you that there is a problem.
From what you're saying, bit flips could happen on Earth, or maybe do happen on Earth, because there is some background radiation. But it's way more common up in space, so you have to do a bit more to make sure it doesn't affect what you're actually doing.
Yeah, cosmic radiation, for example, when you build a data center on high altitude, it's been known that you have to care about this. That you may get more bit flips and other things, right, over there. But Computer hardware these days are designed to handle these, right? Up to different levels. And you're right, as you go up to the space station, the radiation goes up. And then if you go beyond the space station, radiation goes up even higher, albeit that it can't be exposed out there to the level that the astronauts can't tolerate. But whatever the astronauts can tolerate, this computer must tolerate, and that level is higher than background on Earth.
And so, to solve the bit flip problem, the team focused on autonomous software. And to tell us more about that is former software lead for Spaceborne Computer One, Mark Fernandes.
Up until Spaceborne Computer, nearly everything sent to space went through a process they call hardening. And it is a long and expensive process. It can take 10 years or so and cost millions of dollars, right? Many of the computers on board the space station today were put up 20 years ago. Well, when you go to Moon or Mars, you want to take that modern software with you that's only going to run on modern computers. Now, we introduced this concept called hardening with software. And we took a relatively obscure process that's available in NASA and applied it to Spaceborne Computer Two. We did what was called a consequential design rather than a preventative design. Hardening, changing the processor and making sure that it can handle a certain type of radiation so that you can prevent errors. And that's your goal, right? Well, consequential programming and the consequential paradigm that we use says, I don't care why that memory failed. Did it fail because of radiation? Did it fail because it got shaken? Did it fail because it just wore out? I don't care. What's the consequence of me losing that piece of hardware? And we programmed a suite of tools, and we called it hardening with software. We looked at all of the physical systems, and we have a state table of how they can degrade and what we do if that happens and what we do when they fail.
The idea behind this is that by applying this autonomous software, the computer can then look at those errors and then correct them on its own, and even throttle critical systems to prevent potential damage to itself. Pretty clever stuff.
So one scenario could be that during high radiation events, the autonomous software could slow down so that it can cope better with increased errors. But the system is still getting high error correction rates. Perhaps it will tell the astronaut to say, I'm sorry, I had to shut down before I break, because I need to be there for you, right, on your 2-year mission to Mars, then back. Unlike hardware-hardened, mission-critical life support system and so on computers that needs to run all the time, right? The Spaceborne computer is meant to run standard off-the-shelf software, and there will be times where it thinks during extreme high radiation events that it needs to shut down. That's the reason why autonomy is important.
Spaceborne 1 launched on the 14th of August 2017, and it hitched a ride inside SpaceX's Dragon X spacecraft. And after exactly 1 month of being in storage on the ISS, the day finally came in September for it to be properly installed and powered up. A process which sounds much more intense than your average boot up on terra firma.
Finally, it got unloaded, and the astronauts were scheduled to install it September 14, 2017. It removed the bubble wrap, put it into the slot, plugged in all the wires and then the cooling nozzles and all. And we were there sitting on Earth, sweating like crazy, because the first worry was that the vibration of launch. Has anything shaken loose, right? The astronaut flipped the power on and it came up. Wiping sweat all off our brow. That was the first big test. Then there were people commenting that this thing is not going to last a week or two, right? Because of the high radiation events, and it ran for more than a year.
Wow. I mean, that's incredible, isn't it? Having, doing something that's never really been done before and having it run for a whole year. That's pretty cool.
It was a hair-raising moment, right? Each extra day it ran, right? We were wondering. And in fact, the original mission was planned to be 1 year running intensive tests, right? Stressing the CPU, stressing the memory, stressing the storage. But because the return mission was delayed, right, to bring the computer back, it actually ran for a total of 585 days, It was on the station, operational for 585 days. Yes, with interruptions in between, right? For the full 585 days. And if you also count the time it was sitting up there, not switched on yet, it spent 615 days in space. Yeah. The reason I picked a year and then it ran for 1.6 years, right, is because, it takes months to travel to Mars. And then you may want to spend quite a bit of time on Mars after spending months getting there, right? And then there is also the return journey, which is months, right? We're talking a year plus or more for a human mission to Mars. So we want to test the computer for that long, right? Although the conditions further out from low Earth orbit ISS, the ISS low Earth orbit, will be harsher than on the space station, but we felt that this is the first step.
So the hardening with software worked. Woohoo! The autonomous error corrections came back with 0 errors, and even though the odd failures and faults occurred, they were able to circumvent without corrupting any results. And the raging success of Spaceborne 1 didn't go unnoticed by NASA.
So we splashed down in June of 2019 with Spaceborne 1. Before we even splashed down, NASA had asked us, can you go again? Can you go Spaceborne 2? And we began the work then.
Spaceborne 1 had proved beyond doubt that you could indeed put an off-the-shelf high-performance computer into space, and that it could operate as successfully in orbit as it could on Earth. Mark Fernandes became the Principal Investigator for Spaceborne 2 at HPE, building on what he'd learned from Spaceborne 1.
Spaceborne 1, in retrospect, was a proof of concept on the hardware, on getting something in a rocket, getting an astronaut to install it. Will it work? Can you harden things with software? So now we have a proven platform, if you would, upon which we can provide services. And Spaceborne 2 is all about services to the rest of the space community.
Well, services to the space community does sound like a very cool and a bit like a futuristic reason that you could get a knighthood. But joking aside, Spaceborne 1 represented a monumental step in space travel. Because if a supercomputer could survive on a spaceship for an extended period of time, then astronauts could be more self-sufficient, relying on their computer for important decisions, rather than phoning home and dealing with the increasing delay as they drift further and further from home. And this leads us to our current work and HPE's big experiment, edge computing in space. Because, as they say, in space, no one can hear you call for like 20 minutes.
One of the purposes of Spaceborne Computer 2 is to prove the value of edge computing, regardless of where that is. And we are embracing that. More specifically, and the secondary mission, as you say, is when our explorers push that edge further out to the moon and to the Mars, we want them to have the experience and the confidence that the computers they take with them are going to enable them to achieve their mission. We have no computational requirements of our own that we're imposing on Spaceborne. It is all available for the community to do whatever they need to do. So you're looking at quite a distance in which you need to transmit data back and forth. You really want to reserve that for the essential data and let the science, the STEM, the science, technology, engineering, and math data that our scientists are going to be doing on the moon or Mars be processed there. We like to say that the purpose of edge computing is not data collection, but insight. And if we can process that data at the edge to deliver insight, which in generally is much, much smaller, it's a yes, no, go, no, go, no, go type thing, then we can download that insight much more confidently and much more faster than the raw data that you process.
What kind of latency or what kind of transmission times are we talking about on the moon and on Mars?
Well, let me give you some real data from the International Space Station. The latency is 700 to 900 milliseconds. And so it's like going back to the days of a modem when you took your telephone headset and plugged it into a spongy little modem thing. When I'm communicating with Spaceborne 2, I type and must wait for the reply. It's about like that.
And so what about the transmission times if there was, even if it was just radio communication to Mars or to the moon, what kind of time? How long does it take from a round trip?
So we recently did an experiment, and the principal investigator was downloading about 1.8 gigabytes of data, and it's taken him about 12 hours. And so in his mind, it's a half a day to get the data down. We did his processing. We took his software from his lab running on his computers, and we put that software on Spaceborne Computer. We processed that 1.8 gigabytes of data in about 6 minutes, and the resultant insight was downloaded in 2 seconds. So I'm going from half a day to 6 to 7 minutes to get answers back down to the scientists on Earth.
This impressive speed means that astronauts won't need to wait around for answers, allowing them to do more science. And the efficiency of processing data on high-powered computers at the edge will affect how scientific projects work with that data. Scientists will no longer need to send huge amounts of raw data down to Earth for analysis. Instead, it can all be done on board, meaning only the valuable and much smaller InSight data needs to be sent back to Earth. Pretty cool stuff. So, what kinds of data-heavy experiments are they actually doing in space? Well, to find out more, I called up Dr. Timothy Lang.
I'm Timothy Lang. I am an aerospace technologist at NASA Marshall Space Flight Center in Huntsville, Alabama. And I am the mission scientist for an instrument on the space station called the Lightning Imaging Sensor. It's a NASA instrument, but it's part of a Department of Defense space test program payload mounted on the space station right now. It's an Earth-observing payload. It looks for lightning at a particular optical frequency. It's 777 nanometers. Essentially, it's a high-speed camera that takes like 500 frames per second, and it looks for lightning by essentially differencing individual frames from sort of a long-term running mean of what the image that we're looking at is. And based on that, it can detect lightning. The reason it uses this 777 nanometers, that's in the near infrared. It turns out that the lightning signal there is quite strong due to oxygen emission within the lightning channel. The lightning signal is quite strong relative to the daytime solar reflected signal from clouds and that sort of thing. And so you can actually pick up these transients in the optical, even though normally you think it's hard to see lightning during the day. But in this case, if you look at the right frequency, it's actually at least very possible to detect lightning with fairly high detection efficiency.
So why is observing lightning something that we want to do? Why is it important?
Yeah, so lightning is essentially a signature of deep convection. That's convection that basically goes all the way up to the tropopause, top of, or the base of the stratosphere, essentially, sometimes even penetrates slightly into the stratosphere. And so where you see lightning is usually where you're seeing convection like that. And convection like that has a lot of impacts, not only locally, like your weather, severe storms, things like that, but also just climatologically, it's the latent heat or the heat that's released from these big towers that produce a lot of lightning are actually important for just the powering the general circulation of the atmosphere. Lightning is related to the presence of ice, precipitation size ice within a cloud. And so you can actually use information from lightning to sort of deduce the structure of a cloud. And that's important for understanding weather, climate, and various other issues. One last thing is lightning also produces nitrogen oxides, NO and NO2, and those regulate atmospheric ozone through a fairly complex chemical reaction. And it's one of the major natural sources of nitrogen within the nitrogen cycle. So you can't necessarily close the nitrogen cycle unless you figure out what the lightning contribution is.
So, how is the lightning data collected? How does that work, and how does it make its way back down to Earth so you can presumably analyze it?
So as I mentioned, the lightning imaging sensor, or LIS as we like to call it, is essentially a high-speed camera. So it takes 500 frames per second. It's just taking pictures that fast. And essentially what we do is we have computer code working in the partially on board and also in our ground system, our ground processing system. We have computer code that kind of differences these images, these successive images. And when we start to see something spike above sort of the running mean that we're seeing at a particular pixel, we flag that as a transient. And sometimes that's just radiation noise. Sometimes it can be glint from a cloud or from the ocean surface, for example, or snow. But many, many times it's lightning. And essentially it's the optical signal from lightning escaping from the cloud. And so we have algorithms that look for these differencing between frames, and we try to determine whether that's radiation versus glint versus lightning. And the lightning we then further process, because what we see are individual events, and so we kind of link those together when they occur spatially next to each other, and they call those groups. And then when groups occur in a coherent pattern, we can call that a flash. All that flickering. And so the individual events and groups are sort of the individual flickers that we're detecting. We're trying to consolidate that into a coherent product, like a flash.
So how does that data make its way back down to Earth?
Yeah, I mean, this particular instrument is not that particularly high resolution, but we still get like 4 kilometer resolution, or are able to see about like a 600 kilometer swath on the Earth. And we just kind of observe that. And when something pops up, that's what we make note of. But in terms of getting the data down, and normally what we do is we download the data through what's known as the TDRSS, which I believe is it's a series of geostationary satellites that NASA puts up that kind of gets information from things like the space station and other satellites, and then transmits it down to Earth. That goes into the Payload Operations and Integration Center at Marshall Space Flight Center. That basically hosts all the payloads. Essentially, it manages all the payloads for the space station here at Marshall. And then we have our own little command center that's associated with LIS instrument only. And we grab the data from the POIC, or the local payload center for Marshall, get those data, and then we process them on our ground system here and put the data out on these on a NASA data server.
So what are some of the uses for the data that you're collecting?
One nice thing about being on the space station was we also get near real-time data, so kind of like a 2-minute latency. We can get data down and products produced. And that means we can provide data to end users that need data in near real time. That can include weather forecast offices. We've had some collaborations with like the Aviation Weather Center, Ocean Prediction Center. We're a big part of the GOES-R program, where that's the GOES satellites, the geostationary weather satellites. Those now have lightning sensors on them as well that are kind of built on the LIS heritage that look at the whole hemisphere, over the eastern United States and South America and that sort of thing. And so we help validate those data, because from geostationary, the detection of lightning is even more complex. So it's helpful to have a known technology to help support that and help validate that and figure out where does the GLM sensor work well and where does it not work well. And that information can be provided to forecasters for interpreting what they're seeing.
Well, it certainly sounds like lightning strike analysis has a ton of useful applications, particularly for climate science. And although his work doesn't currently use Spaceborne 2 to process the enormous amounts of data captured by Liz, Dr. Lang says that it's something that he could potentially see happening in the future with his own and others' projects. And not only could supercomputing at the edge process different datasets separately, but it could develop greater insights by collating data from different studies.
Yeah, so, well, even just the existing missions on the space station, what gets sent up to the space station to do Earth observations is kind of a hodgepodge of different missions. But occasionally, those things have synergies, like synergistic capabilities. Like you could have, like what's going up soon is a series of microwave radiometers, which are sort of passive sensors that look in multiple different microwave frequencies. And that can help you sense precipitation and various characteristics of clouds. Well, if you integrate that with lightning information, you get a lot more information about what's actually going on internally in a storm. But that's going to take processing power to be able to integrate those data properly. And generally, it's best to kind of do as much onboard processing as you can so you don't have to transmit as much data to the ground. You can send like a reduced amount of data to the ground for processing. And that's where like having onboard high performance computing could really, really make a difference. And just in general, like these NASA likes to do integrated satellites like this TRIM satellite that had a lot of different sensors on it, or the space station with a collection of different Earth observations. And there are future missions that generally, it's not just one satellite, one instrument on one satellite, it's like many instruments on one or more satellites, all working towards a common purpose. And you can imagine like you could try to download all those data, but that costs a lot of money to download all those data, and then you got to do all the expensive processing down the surface. But what if you could actually do that processing up in space and send down reduced products that really would save the amount of time and money you need to have these sort of data downlinks?
Yeah. So is it something that you could see being part of the project, the mission that you're working on?
Yeah, potentially part of lightning imaging sensor in the future, but also, like I said, this was an older mission, but we're always looking towards the future here and to do some kind of the next cool thing. And so we're looking at a lightning mission that would, potentially have multiple cameras and multiple frequencies, different frequencies to get more information. Possibly use, in addition to optical, also some radio frequency detections of lightning. And so that's a lot of data, and trying to figure out how best to combine that. That's going to require complex algorithms, a lot of processing power. It's possible that you would want to do as much of that as you can up in space. And so having high performance computing, or even just lessons learned from these sort of demonstration missions like HPE and whatnot, are things that can be applied to these new missions to get better data products out of them.
Thank you, Dr. Lang. Incredible stuff. Now, there's experiments going on all the time on the ISS, and it's not all focused on what's happening down here on Earth. There's the Sound C tests, which monitor the sounds in the ISS to detect anomalies in equipment. There's the Functional Immune experiment, which looks to determine what changes take place in crew members' immune systems during flight, and the list goes on. And Mark Fernandes reckons there are a ton of opportunities for these experiments to really take advantage of edge computing.
One is the DNA changes of the astronauts. You know that DNA sequences are really, really large. They define the entire human there. But the changes between your normal DNA from a week ago and your DNA today may be very tiny. Well, the processing capability to find that difference is well known. And we moved that software up to Spaceborne Computer Two, and instead of this massive DNA sequence, we bring you down the difference. Another image processing, if you would, inside the space station hits the manufacturing vertical and the life sciences vertical. One is you're growing potatoes on Mars, and you notice something strange about this potato. Is it a mold? Is it something odd growing on it? And maybe that could be identified photographically, and you take a high-res photo of it, and you've got stored on Spaceborne Computer a database of potato anomalies, and you want to do that image comparison and find out if that potato is safe to eat and turn into your French fries, correct? Another one is you've used a 3D printer to print a tool. Well, you kind of want to know that it was printed properly and it's safe to use this tool. You just don't want to take it out of the 3D printer and begin to use it. There are X-ray and infrared and other types of scans that are done on 3D printed items, and then those images go through a QA/QC process and then give you a thumbs up or a thumbs down on the instrument. So again, all you want is a thumbs up or a thumbs down. Can I use this instrument? You don't want to send megabytes or gigabytes of video and imagery all the way back to Earth to have that thumbs up or thumbs down. We could do that on Spaceborne too.
I like the potato example because that's very The Martian, isn't it? So can you talk me through how Spaceborne 2 is being used with scientists on Earth? Am I right in saying there's some sort of proposal for experiments?
Oh, yes, it's wonderful. So for information, you go to hpe.com/info/Spaceborne. And that page will be full of lots of information about Spaceborne Computer. But if you scroll down, there's a little section that says, would you like to run an experiment on Spaceborne? And it begins with a simple email. I've been describing us as Switzerland. We're neutral. We want all explorers, all researchers in all verticals to learn of the power of edge computing. HPE has a part of its culture an emphasis to be a power for good. Our evaluation of all those submissions has a 6-point scale. And you're asked to address where do you fit on this scale. And the scale is this going to benefit you? Or is this going to benefit your organization? Number 3, will this benefit your scientific or engineering community? Number 4, will this benefit NASA? Number 5, will it benefit space exploration, which goes beyond NASA potentially? And number 6, will this benefit humanity? So you can understand how a lightning strike analysis might be of value. Polar ice cap analysis might be of value. DNA sequencing processing, our astronauts will have shown how they can do that DNA sampling, how they can get it to a small spaceborne computer, an edge processor, if you would. And we've shown how we can use satellite communications to get that back to the doctors that matter. And we'll soon have satellite connectivity globally.
So Spaceborne 2 isn't the only exciting technology making its way into our orbit. Mark says that satellite communications are seeing a lot of investment as scientists really start to push the limits of what's possible and rethink how we use these instruments. Although what Mark is most excited about is how Spaceborne 2 could play a part in this evolution of satellites.
There are a lot of ambitious satellite plans coming, and they involve lots of satellites, almost a swarm of satellites. One of the plans is to simulate a satellite swarm and do satellite swarm processing. Another experiment plan is satellite-to-satellite communications that is ultra secure. So you want to minimize the communications between the satellites, and you want them to be secure. So that's called software-defined radios. And when you have a software-defined radio, you don't have to go make a new radio, a new antenna, a new anything. It's all done in software, and you can tweak the frequencies and the encoding and the encryption, et cetera, until you come up with something that you're good. And you can do lots of those software-defined radio experiments. A third one to me is kind of exciting, and it was explained to me that physical weight is one of the big limitations in sending up satellites. So it would be more advantageous to send up a lot of smaller, lightweight satellites that didn't have much power, not enough power even to send a signal to Earth, but in space, they could send a signal to a mother satellite powered by Spaceborne Computer Two. Those would be secure connections, and we could process that data on Spaceborne, extract the features that you're interested in, and then with a secure downlink, get those to Earth to whomever needs them. So that is also one of the concepts that's in discussion for Spaceborne.
So how long is the Spaceborne Computer 2 program going to last for? What's the long-term plan for it?
Well, Spaceborne 2, after successfully proving our concepts with Spaceborne 1, NASA said, we want you to have a mission that is approximately as long as the first plan's missions to Mars. So we are nominally down for 2 to 3 years. And I'm pretty confident our hardware and software will last that long, and we'll see what comes after that.
Spaceborne 2 was sent up to the ISS on the 22nd of February 2021, and it was powered up on the 6th of May, and is now operational. If you want to follow what it's up to, we'll share a load of links to some of the cool experiments it's working on in the show notes. Now, while Spaceborne 2 is streaking through the night sky on board the ISS, Spaceborne 1 is on its way to the Imperial War Museum in London. So, with the original taking its place in the annals of history and the successor already fired up for the next mission, I asked Eng Lim what he thought both computers represented for edge computing, AI, and their place in the future of space travel.
Yes, this is an insightful question, right? Both of them, right? I think Spaceborne Computer One, Spaceborne Computer Two, and the vision is to continue with this with other Spaceborne computer projects as we progress towards supporting human mission to Mars and beyond. They are pivotal in demonstrating that astronauts, their self-sufficiency can be greatly enhanced by having high-performance computing power that is off the shelf available to them on board during their long-duration space travel. That's the key principle to which we've been working hard on to support astronauts on. Their self-sufficiency, right? Self-sufficiency includes many things, and one of which is having computing power, immediate guidance and answers while waiting for answers to come to them from Earth. That's going to be a delay the further and further away they are from Earth. Yeah. So SBC, Spaceborne Computer, this program, right? 1, 2, and hopefully more, the program is pivotal in demonstrating that self-sufficiency is possible to this extent.
Spaceborne 2's ability to look after itself, look after astronauts, and conduct edge processing at the extremest of edges is already an impressive feat. So, with both computers representing such great successes, what on, or off Earth, comes next?
We have a blue sky goal, which is right out of the AI machine learning realm, if you would. We're kind of tracking all these different experiments and how long they take to run on Spaceborne versus how long it takes to download and run on Earth. And at the extreme example, I may have something that needs a cloud-based supercomputer to come up with the answer. Yes, I could do it on Spaceborne Computer, but it would take an amount of time. Well, the AI ML would look at these and say, is the compute time on Spaceborne less than the download time to the cloud? and then have the cloud get the answer quickly and then upload the answer. And so again, we want to off-burden our scientists and engineers and explorers and give them the confidence that we can get their answers. When they need to do something, Spaceborne Computer can sit there and use its AI/ML and say, I can get this answer faster if I burst down to the cloud. Or I think I can do a better job if I keep it here on Spaceborne and give them an estimate of when the answer will be around. So that's what we're kind of working toward as a blue sky project.
And it sounds like something the Spaceborne team can certainly make happen.
I didn't dream of achieving this together with the team. It was a progressive thing, right? It started with NASA being our customer, supporting them with high-performance computing, and then realizing that they will need similar compute power with them, at least on a smaller scale, right? With the astronauts as they go further and further away from Earth. And there is this need. Let's address it. And then here we are today, right?
And so ends our foray into tech in space. Spaceborne 1 and 2's travels into the very near cosmos have revealed that hardening through software could just be the next big thing in getting sophisticated, up-to-date instruments into orbit and beyond, negating the need for lengthy and costly physical shielding. The Spaceborne program has also demonstrated the important role high-performance computing will play in space travel moving forward. It will allow astronauts and scientists to process data at the edge to gain insights faster than ever before, enabling researchers to achieve more and potentially saving astronauts precious time when it comes to making critical decisions. And all of these innovations might just be helping to push humanity that little bit closer to a mission to Mars. But whether the next Spaceborne helps humans to sequence DNA on our way to Mars, or warn us of dodgy potatoes, let's just hope it can open the pod bay doors when asked. You have been listening to Technology Untangled. I'm your host, Michael Bird, and a huge thanks to today's guests, Eng Lim Goh, Mark Fernandes, and Timothy Lang. You can find more information in the show notes. This episode was written, produced and edited by Isabel Pollard and Ryan Sutton, with sound design and mixing by Alex Bennett and production support from Harry Morton, Alex Podmore, Tom Clark and Sophie Cutler. Technology Untangled is a Lower Street production for Hewlett-Packard Enterprise. Thank you so much for tuning in, and we'll see you next time.